and I'm going to talk about things like cryptography and distributed systems and economics, and like each of those subjects is a galaxy unto itself, in and of itself. So there's obviously going to be a lot of compression and simplification of some of these concepts. I've got some resources that anyone who's interested to learn more, I can point you in that direction. But just to set the expectation, I'm going to give a really high-level overview of this stuff to hopefully drive a conversation, help, for the Q&A, to give you all kind of the chance to ask questions about what your specific interests are, or something, some gap that I didn't cover. Second disclaimer is, I made these slides, and anyone who knows me knows that I'm not like a design person, so hold your applause when you see all my amazingly designed slides. Yeah, and then finally, as I mentioned kind of in the beginning, this is a pretty big oversimplification. If you're a person with a deep technical background, I understand that you may have a slightly different definition of what a distributed system is. In the interest of the flow of the presentation, just hold all that till afterwards, and I would love, actually would love your input and what you think that is, because I work, for those of you that don't know, I work actually for Andreessen Horowitz on their crypto fund, and one of the projects that I've done there is create a glossary for everyone, a glossary of terms for everyone to help understand this technology. So I'd love your input. Just please don't interrupt the presentation for the benefit of other people. Cool. Hey, Chris, what's up? Okay, so I'm just going to talk amongst yourselves here for a moment. I'm going to get set up AV-wise, and thank you all for coming. Okay, so like I said already, the purpose of this is to be an introduction to these technologies of cryptocurrency and blockchain. So I'm going to kind of talk about at a high level what they are, and then I'm going to kind of dive a little bit deeper into what is the technology or concepts that enable this innovation. And then I'm going to kind of zoom out at the end and say why I think you all should care, and why I think it's revolutionary, and why I chose to dedicate my career to this tech. So, okay, with that, so I think the simplest thing is I'm going to give you a definition of what a blockchain is. Again, there are a whole galaxy of different definitions, but this is mine. And I'll kind of break it down here. A blockchain is a permissionless, digital, tamper-proof, distributed ledger secured using cryptography and organized into a series of data blocks. Okay, so anyone could add blocks according to the consensus protocol, but then it's append only, which means that blocks once added can never be deleted. Okay, so I'm going to go through each of these in turn, and we'll kind of think about, or hopefully by the end of this you should understand kind of each of those individual pieces and how they come together to create a blockchain. Okay, so here's some cool iconography. I think one of the things, actually I want to highlight all three of these things. Even though Bitcoin, in 2009 was the first instantiation of a blockchain, and it's viewed as a revolutionary and incredibly innovative technology, most of the ideas that underpin blockchain and cryptocurrencies are pretty old. It's not actually there's no technological breakthrough. The main breakthrough was just a recombination of some existing ideas and technologies in a novel way. So that's one point I want to emphasize. The other thing is, a lot of times when we talk about blockchain and cryptocurrencies, there's a lot of different people from different backgrounds that have varying interests in this technology, and frankly, sometimes the discussion can become a little bit political, in that, it's just kind of like a very libertarian type of thing, right? Where it's in the same, kind of in the same, or I guess for the reason that it's sort of a derivative of cryptography, it really empowers individuals, and disempowers kind of centralized entities. Hence the term decentralization. That's why you hear it all the time in blockchain and cryptocurrency. But I want to tell you, and I think it's true, that with regard to blockchain and cryptocurrencies, decentralization exists along a spectrum, right? So it's not like a binary thing. It's not like it's either all decentralized or it's all centralized, right? The systems that we architect, technological, political, or otherwise, invariably, the design choices invariably reflect different people's preferences around how much trust they want to centralize into a single entity and how much they want to reserve for the individual. So it's not a binary, it's a spectrum. lastly, this is something that the revolution is that this architecture creates like a completely new economic paradigm. If you're just talking about Bitcoin, which is, Bitcoin was originally designed to be a peer-to-peer digital trustless currency. But if you take those same ideas that enable Bitcoin, you actually get an entirely new type of computation, or like a new type of computational paradigm. And that's pretty amazing, right? I think that's on the same level as, frankly, the internet, in the same way that the internet revolutionized computation and the way we interact as a society. I think this technology has the potential to do the same thing. Okay, so kind of rehash here. So this is like some of the technical stuff that actually goes into the secret sauce that is blockchain cryptocurrencies. I'm breaking it down into 3 buckets. You have cryptography, you have distributed systems, and then economic incentives. And I'm just going to highlight here, we have 2 incredibly smart members of the Stanford Blockchain Club, Andrew Tam and Jorge, who I already introduced. These gentlemen are both Stanford CS, elite technical members of Silicon Valley. So for deep questions about cryptography and distributed systems, direct it to them, because they actually are the experts. So, but I'm going to give a high-level overview, and I'm going to kind of take these in turn. Oh, yeah, I want to talk about this. Yeah, so I mentioned that blockchains, like the whole kind of beginning of this technology was really like this desire to create some kind of peer-to-peer digital currency, right? And interestingly, even though Bitcoin came out in 2009, like there's been attempts to create a digital currency since the 80s, actually. There's something called e-gold, digicash, hashcash. Most of you probably don't know what those are because they were complete failures. They were never adopted for a variety of reasons. And this slide here kind of shows like some of the problems with taking, traditional payment system in the real world and translating it to the digital world. And really what the primary problem is the fact that like there's no such thing as physical scarcity in the digital world. How many people here have illegally downloaded a song from like Napster or like BitTorrent or anything? Yeah. All right, yeah. You're all lying. I know you're lying. You all have. Okay. But that's the point, right? Like there's no, unlike a compact disc, right, where it's like there's a physical compact disc and then like it's in a store and like unless you steal it from the store, you have to like purchase it. Like these songs on the internet are just ones and zeros, right? There's no, like you can copy and paste it as many times as you want. That's sort of the problem in general with digital systems. So how do you create this digital scarcity? And the way that things like PayPal work, or Venmo, et cetera, is you have this basically a trusted intermediary that sits between you and the person that you want to pay, and they essentially track all of these things for you. Now that actually works great. I don't think anyone here has complaints about Visa or PayPal or Venmo. I certainly don't. But again, the important assumption there is that you're trusting that middleman to ensure that they actually are processing your payments, right? So I'm going to talk a little bit more about that at the end. I don't want to dwell on that, but I just wanted to kind of track for you guys the evolution of these ideas and how this, Bitcoin is kind of the end of a long road of failed attempts to try and create a decentralized digital cash. Okay, I'm not going to dive into this slide, but I just reemphasize, it's more than just payments, right? Like you can take the same ideas and use it for computation. Okay, so I'm going to jump into a couple of building blocks here. Okay, cryptography. So cryptography's been around forever, like literally. As long as people have been communicating with each other, there's been people who want to hide what they're communicating to a person from other people, right? And so that's essentially, the entire field of cryptography is all about that, is to communicate securely between 2 or more parties, right? And so the 3 kind of properties that we look for in cryptography or cryptographic systems for security is this idea of privacy. So like the message that I'm exchanging with someone else, no one else can read but that person, right? Integrity, which is that the message that I receive from like Jorge, I am confident that that is the actual message he sent, and that somebody didn't just like scramble it or mess around with it along the way in the middle. And authenticity is that the message I got is actually from Jorge. So I know that it wasn't like switched out in the middle like Andrew, and like Andrew switched Jorge's message with his own. Say like, hey, like Jorge sent me a message like, you owe me $5, and Andrew switched out and said, you owe Andrew $5, right? So that's the idea of authenticity, to ensure that you know who the sender and receiver are. So I'm going to talk specifically about a couple of, like I said, this is an entire subject in and of itself, and I'm going to plug it again at the end, but I want to do a plug here for if you're interested in this topic, which you all should be. It's incredible, and it's incredibly relevant for the internet age in which we all live. I'm going to put a plug in here for Professor Dan Bonet in the Computer Science School. Teaches an incredible class on cryptography, and I insist that you take it. And if you don't want to take it, if you're not a student, he's also got a Coursera course that covers a lot of these concepts in great detail. Okay, so I'm gonna skip over like 99.99% of cryptography. I'm only going to tell you what's relevant to blockchains and what part, like going back here, how they are secured using cryptography, the specific cryptography that's applied in blockchains. So. All right, jumping forward, the most important form of cryptography as it relates to blockchains is these things called hash functions, right? So hash functions are these special mathematical programs that help us ensure the integrity of data. So this is like a lot on the slide, and it's kind of like, there's these 5 things that hash functions do, and I think these are important details. I don't want to gloss over this. I want to make sure you guys understand, because these are really, hash functions are essentially the workhorse of modern cryptography. And understanding why they work the way they work and what they do is incredibly important. So a hash function, like I said, is just a special program. And basically this program has 5 properties. And you can see them here. So number 1 is deterministic. That means if you put something into the program, and if you think of an input, just think of like something you type onto your keyboard. So think of this as a computer program, and an input is something you type onto your keyboard. So every input that you put in results in the same output every time, right? So this contrasts to like some kind of like random program, right? Where it's like you type in something and a random thing comes up, right? So this is the same input always results in the same output. It's not invertible, which means that if you just see the output, you have no idea what the input might have been. Like, it's impossible for you to work backwards from the output to get the input. It's collision resistant, and basically what that means is, like, most of the time hash functions have this compression property where your input could be super, super long, but the output is going to be kind of short, right? So let's say you have an input, and you want to input like 500 words, and the output, potentially is like a word, right? Or like a string of characters that's like 32 characters long. So collision resistance essentially means this idea that, like, even though you have this massive, massive galaxy or set of possible inputs, and the set of outputs is relatively small, it's still big enough to mean that there's pretty much no likelihood, probabilistically, of a collision, that 2 inputs are the same output. Okay, unpredictable. So this kind of ties back to something I said in the first bullet about deterministic, where, like, okay, the same input always results in the same output. Well, you also want this program to be unpredictable, right? For cryptographic purposes, you want to make sure that, for all intents and purposes, anyone looking at like a set of these outputs, it looks kind of like random numbers, right? You don't want there to be any kind of pattern. So if, like, you have an input, let's just say you input 1, 2, 3, 4, 5. Like, that output from the hash function should look completely different than 1, 2, 3, 4, 5, 6, right? So, like, even a tiny change in the output, or excuse me, the input, results in a huge change in the output, right? So that's sort of like this idea that it's kind of looks random. And then the last thing is efficiently verifiable. And that means that it's super easy to check. So it's really easy to check. Actually, I'm sorry, this should be efficiently computable. Efficiently computable is that, yeah, basically it's relatively easy to compute what the result of it is. Okay. Efficiently verifiable applies to something else I'll talk about a little bit later. Okay, so the takeaway is you can use this thing to create like a tamper-proof data storage, right? So, and I'll tell you how. Basically, you take data that you want to make tamper-proof, and you run it through a hash function, and you get an output, right? And then you can always check, actually, to see if the input that you get next time is the same as that output, right? This is actually how passwords work on the internet. For those of you who don't know, if, like, you enter your password into a website, that password actually is not sent over the internet, quote unquote, in the clear. It's hashed first, which is to say it's put through this function, you get a kind of a random looking output, and then it's compared against a hash value at a server, right? And so if your password is not the same, and that hash of your different password is compared against the hash in the server, it's going to look completely different, and so the tampering will be detected. So hash functions enable tamper-proof, or like essentially tamper-proof data structures. Okay, so I just tried to do like a practical example here. So SHA-256 is like a pretty common hash algorithm used on the internet. And so I just took, and this is like real outputs and inputs, by the way. So I took like 3 sections of the Declaration of Independence, and I ran it through the SHA-256 hash function. So a couple things I want to highlight here is 1, the inputs, 1, 2, and 3. 1 is a different length than 2 and 3, right? But you can see the outputs are the same length here. 2 is the inputs for 2 and 3 are actually almost the exact same. I highlighted the only difference. The only difference is I changed the capitalization on one word. And by the way, actually, sorry, the input here in 2 and 3 is not just these words. I took the entire Declaration of Independence and pasted it in and ran it through this hash function. So it's like a whole document, all right? And so you can see here that only 1 letter capitalization difference resulted in a completely different output, right? So that's one of the really important properties about these functions that I wanted to highlight here. Okay, the next piece I want to talk about is public key cryptography. Okay, so public key cryptography is basically the way we ensure authentication, which I already talked about, between messages of 2 parties, right? So kind of the way to think about it is public key cryptography is also called asymmetric cryptography, and there's in this paradigm there's like this idea of a public key and a private key, right? And the way I like to think about this is like you have a private key, just like you have a key to your house. A private key is kind of like the key to your house, right? And this public key is kind of like the address of your house. So if I reveal to Jorge my public key or my public address, that doesn't enable him to get into my house, right? Just like if I told someone, hey, I live in, whatever address, that just knowledge of that address doesn't enable them to walk through my front door without my key, right? And so why is this important? Because it enables attribution on digital networks, right? So you can use these like public and private keys, which are just numbers, and as you can see here, this is how they're created. So you have like essentially what is a secret passcode. You put it through this special type of function that's called a one-way function, and you get this public identity. So interesting, it's important to note here that like the mathematical function that you use to derive the public key from the private key is public, everyone knows it, and your identity can be public. And knowledge of those 2 things alone doesn't give you any ability at all to derive the secret key or recreate like the key to my front door, right? And so what you can do is use this to have a scheme where you have digital signatures on messages, right? So really important application of cryptography is to use a public-private key system and show that only a person with a specific private key was essentially signed the message that you're reading, right? So it's essentially a form of attribution. It enables attribution on a digital network. So that's really important for blockchains, right? And particularly for cryptocurrencies like Bitcoin, it's like who sent who money, right? You kind of actually need to know, since it's a ledger at its core, essentially this enables you to track the different parties that transacted. Okay. Next thing I'm going to kind of dive into here is this, our distributed systems. And distributed systems is like a really fancy word for computer networks, all right? Anyone who's used the internet knows what a distributed system is, or at least has used one. And really, the idea is really kind of like, it's a network of computers that's sort of trying to replicate what a single computer does in its own little paradigm, right? So there's kind of 3 problems that distributed computers face, or distributed networks face, that like a single computer doesn't face. And one of those is the fact that like to communicate between nodes, as these different computers on the network are known, the only thing you can really do is pass messages. You're like, okay, well, it's not really a huge deal, because you can pass messages over the internet, who cares? But the problem is, sometimes, if you don't receive a message as a node on the network, was that because no one sent you the message? Was it because the message got lost in transit? Was it because the message was corrupted? Or was it because the node that was supposed to send the message was acting in a malicious manner, right? You don't, these different nodes on the network don't have any ability to discriminate between those scenarios. So actually, it's kind of hard to get to a shared sense of truth among all of the nodes on the network because of these three problems, right? Oh, and I forgot to mention, there's no global clock. It's kind of funny, like in the realm of computers in the digital world, again, there's like an entire galaxy of work devoted to just ensuring that different computers on a network run on the same clock, which is something that we all take for granted, right? But actually, looking around the world, there's, clocks are all kind of a little bit different from each other, and in digital systems that do millions of operations per second, even a microsecond of time difference on these distributed networks can have catastrophic cascading effects. So these are all challenges with distributed systems, and so these all also apply to blockchains and cryptocurrencies because they are inherently distributed. So the two pieces, again, I'm going to talk about for crypto that are relevant is this idea of a peer-to-peer network, and then I'm going to talk about consensus protocols. Okay, so this is just kind of like the difference. Wow, that came out pretty grainy. Okay, so this is like basically two different network paradigms, and I think most of you are probably familiar with this. There's kind of like this idea of like a server-based network, right? And there's like a central server that lives in the middle of this network, and when the nodes or clients that are connected to the server want some data that's stored on the server, they just request it from the server, and then the server sends it back. So this is like very much a centralized hub and spoke is, I guess, as you can see by the picture, essentially what it is. Peer-to-peer network is kind of fundamentally different, right? Where in this network, essentially every node is connected to every other node, right? So I know no one, I already asked the question of who's downloaded illegal stuff, but like essentially all the illegal download sites are peer-to-peer networks, right? So obviously if there was any kind of like centralized server that was hosting illegal content, it would be shut down pretty quickly. So the way these sites are organized is through peer-to-peer networks, right? And so there's no single point of failure. So then it's kind of like, essentially it's a redundant failure, a resilient network, I guess, in that sense. And that's actually like, the internet itself is a peer-to-peer network. And the internet, for those of you who don't know, it's got a fascinating history, but actually kind of the genesis of why the internet was invented, actually, it started at the Department of Defense at a place called the Defense Advanced Research Projects Agency. And the problem they were trying to solve was like, man, we're kind of in this Cold War, and at any point someone could launch, or not someone, the Soviet Union could launch nuclear missiles and wipe out our entire command and control network in a preemptive strike that we may never even know and have no ability to react. And so like, how could we design a communication protocol that could withstand like 90% of our communication nodes being knocked offline, but still be able to communicate between everyone who's left? And that was essentially the genesis of the internet. It was called the ARPANET, and this is actually a picture from 1980. This is, the internet, what, 40 years ago now almost? So you can see there's just a few connections. It's not very exciting, but obviously, again, this is a stupid picture, but all of you know like how important the internet is today, right? Essentially, all of us here are connected to virtually everyone else in the world, or at least everyone else in the world that has a computer or smartphone or anything that's connected. Okay, so consensus, I'm just going to touch this at a really high level, but basically the takeaway is, how do nodes on a distributed network come to the same sense of truth, right? So if you've got, let's say, you've got 4 different computers and their job is to track weather, let's say, right? And they take input data from things like satellites or some other sensor. How do you ensure, and they pass messages to each other if they get some data, just to ensure that all the nodes each have them. So it's how does each individual computer, how do you make sure that they're all tracking the same state of the weather? How do they share that same truth, right? And for a centralized system, this is a trivial problem, right? It's like, well, just ask like the central clearinghouse or the central server, like that's the one single point where all the changes are tracked through. In a distributed network, this is kind of hard. Particularly where you remove any kind of trust assumption, where you assume that, okay, hey, these other computers on the network might not only be malfunctioning, but they might be intentionally trying to screw me over, right? So this is like a really hard problem. So I have this, again, this is like a little bit of silly iconography, but I liken it to a court. It's in the same way that when we have disputes in the real world, we arbitrate them at some kind of court of law. There's a legal system by which we kind of arrive at, or at least from a societal perspective or from a legal perspective, we arrive at what happened. Two sides of a different argument have two different realities of an event that happened, and they go present their arguments, call witnesses, etc., in front of a judge. The judge or a jury arbitrates and says, okay, this is what actually happened based on the facts and circumstances, et cetera, et cetera. And then essentially there's a punishment or there's some kind of consequence as a result of that now shared reality, right? Or at least hopefully shared reality. And so in a distributed network, a consensus protocol, so in a distributed network, there is no judge, there is no central party. And a consensus protocol essentially fills that role, right? So it's an algorithm that makes a series of choices or has parameters which enables these computers to kind of converge around a shared sense of truth. Okay. This is where the iconography gets really good, so hold on to your seats here. Okay, so yeah, let me jump back here. Okay, so we talked about cryptography and we talked about distributed systems, and you should all be asking me, okay, why aren't we done yet? Like, you just told me about all this amazing cryptography that can protect messages, and we've got like these distributed algorithms, like, you know, that enable the internet, and we can like pass, you know, they can come to consensus, and like, why the hell do you need anything else to like have digital cash, right? This should kind of be everything, right? Well, it turns out because of what I mentioned earlier, the fact that in the digital world, ones and zeros are not scarce, that's like almost an intractable problem. Or it is an intractable problem from just a purely technical point of view, right? So, and again, all those failed attempts that I previously mentioned, cash, e-gold, digicash, failed for this exact reason, right? It was like, ultimately it came down to the fact that someone who had a one digicash in their wallet could just spend that same digicash like 10,000 times over, even though it was a single unit of currency, right? Which obviously destroys any kind of peer-to-peer cash system. Okay, so the real genius in Bitcoin was to combine these technical concepts of cryptography and distributed systems with these economic incentives to make the whole thing work. And the first piece of that is called proof of work. And proof of work actually didn't even originate with Bitcoin. This is kind of like a fun piece of trivia. Proof of work was actually proposed by some researchers in, I think it was 1997, as a means to combat spam. For those of you who had email accounts in like the early days of the internet, like, you know, it was like generally 99.9% of your inbox was just crap advertisement, kind of like, you know, mailboxes still are today. You just like get all this crap advertisement, and so essentially proof of work was this notion of like, you know, there's no cost essentially for someone on the internet to just send messages to every email address. And so what if we created a mechanism by which we had to make these computers that were sending these emails prove that they had done some hard computation that kind of takes a while, and then maybe that would mean that they would have way less incentive to just send emails to every email address on the network. So that's kind of the notion of proof of work, and the reason I slaved over this terrible iconography is to kind of like give you the metaphor of like, it really, you know, you guys may have heard the term mining and cryptocurrency. I think it's a really apt metaphor for proof of work, right? So if you're a gold miner in California in the 1800s, for example, and you're working in a mine, generally you got paid by the weight of gold that you were able to mine out of the ground, right? So once you mine gold out of the ground, there's no way to like remine the same gold, okay? So it's like, you know, it's scarce in that sense. So you're paid proportional to the amount of gold that you mine. And it's also really super easy for this manager here to check to see how much gold you actually mine, right? It's like he doesn't have to mine the gold himself to know that you mine the gold, right? He just has to look or like weigh it on a scale to know, okay, yep, you mine the gold, okay, so now here's your payment. So we want these exact same properties for a proof of work system in the digital world. So again, we want it to be hard to do, basically, so we don't want email spammers to be able to just like spam everybody. So there needs to be a cost, so it needs to be hard to do. It needs to be scarce in the sense that just because you've done a computation once, you can't just redo that same computation and get the same reward again. And it needs to be really easy to check, right? So it needs to be hard to do but easy to check, right? So this is a proof of work system. So this combined with, oh yeah, this is, those of you who haven't seen, this is like Bitcoin uses proof of work to verify the state of the ledger. Millions of computers around the world, just like this, do this calculation kind of in the same paradigm that I just described. So they perform this hard computation, expending energy and therefore money to do it, and then they're rewarded. The whole point of doing this in Bitcoin is that you do all this for a reward, right? So no one works, well, in economics, no one works for free. So the idea is that how can we align incentives in this network, in this distributed network where we don't trust anybody? Every individual participant, we assume, is trying to screw every other one as well as take advantage of the system as a whole. So how can we make an economic incentive for people to profit from actually securing the network? And that was the combination of proof of work and then adding in a reward on this ledger of the blockchain, right? So essentially, again, I talked about blockchain is just a ledger, and essentially what this ledger is, it's organized into blocks. And so now we have these participants called miners who essentially can add blocks, and blocks are just transactions, right? So it's like I sent 1 Bitcoin to Jorge, Andrew sent 2 Bitcoin to me, and so these are just blocks that are listed like this. And basically, these are clumps of data that get added to the ledger. And the purpose of the miners is that they are competing to essentially add these different transactions or blocks to the ledger. And the reason they're competing is because each block that gets added, you receive a reward in the form of transaction fees as well as like network inflation. So the network itself will actually mint new Bitcoin, and then will give that newly minted Bitcoin to the miner that added the block. So in that way, and so it's important to note that the data that's added to the block has to be valid, right? And this gets back to the consensus mechanism. So there's a consensus mechanism that says, hey, this is how we track the state of the ledger over time. And so again, getting back to my last little slide here, because this is a proof of work system, I mentioned already, it's easy to check, right? So that if any miner decides to add a block, first of all, they have to perform a hard computation. There's no way to shortcut. And then once they solve that problem or that computation, essentially then they have to broadcast it to the rest of the network, because again, it's a peer-to-peer network. So every individual node has to accept the output. And they're all running the same consensus algorithm. And if that output or the solution to the problem that the individual miner submitted is invalid, the network will reject all those blocks, or will reject that block, right? And why that matters is because that means the miner who submitted the incorrect solution forfeits the reward, right? So they're incentivized, essentially, to submit the right solution and then to receive a reward. And so therefore, in that sense, the system is self-reinforcing. The security system is self-reinforcing. Okay. We're almost to questions, and I know this is a lot of stuff, so if any of you are confused, I'm going to hopefully take, well, not hopefully, I will take questions and I can clarify some stuff. So here's Bitcoin. This is the symbol for Bitcoin in case you guys don't know. So what I just walked you through is like, this got us to Bitcoin, right? There's, I think, since I work in crypto BC, I should know this, but there's around 2,500 other cryptocurrencies that are relatively, I would say, that have any kind of significant market cap that exist today, right? So this is just one. This was the first cryptocurrency that came into existence in 2009. And today there's thousands, like I said. So again, this is just, the purpose of today is just give you guys a flavor, an introduction kind of into this world, and to encourage you hopefully to kind of learn more about it. And again, like I said, the idea of financial exchange between two parties is really just the beginning, right? Because if you think about a ledger, well, actually, don't think about a ledger. Think about a computer, right? Ultimately, a computer is just a system where, it's sort of processing transactions in and of its core, right? If you like boil down what happens inside of a computer, it's kind of just ones and zeros getting passed around, right? And so if you take this idea to like, okay, instead of transactions, what if I executed a piece of code in the same manner that I like transferred, it's like instead of saying like, I sent Jorge 1 Bitcoin, what if you expand the syntax of this program to include all kinds of different things, really anything that you can dream up in like a legal document, some kind of contract or anything. So there's this whole galaxy of possibilities that's opened up. And why is this important? Because unlike a traditional computational paradigm or a traditional computer, like this is a computer that is like essentially, it's trustless. It requires no trust assumptions, right? So this is a slide I stole from Balaji Srinivasan, who's a former CTO of Coinbase. So there's a little bit of Coinbase propaganda in here. But basically, like the important thing is this whole system and this paradigm gives you a choice of who to trust. And this gets back to the spectrum of decentralization that I talked about earlier. It's not that you just you have to live in either a trustless world or a world where you trust people. But now this technology enables you to have the choice about whether or not you want to trust any particular entity on the digital network, which again, I can't emphasize enough, never existed before, right? So like Facebook, for example, if you want to go on and update your profile on Facebook, you want to read anybody's information, you're trusting the Facebook servers are giving you that proper information, are updating the information in the way that you want to do. And obviously they have every incentive to do that because it's their business model, but not every centralized system is benign or even benevolent, right? And there's many places in the world where that actually doesn't exist. Like here, right? So there's some Syrian refugees fleeing from, as you guys know, there's a civil war in Syria, and over 1 million people have been displaced. About 150,000 people were killed. And so a centralized system, I guess let me back up. So I think in a place like the United States or in Europe or in the developed world in general, most of the time, I think most people I talk to are like, why the hell would I even ever consider using Bitcoin? I have dollars and that works just fine to me. And I agree, I mean, it works fine for me too, but I think we have to acknowledge that in many places around the world, that's not the case for individuals, right? In places, and for those of you who don't know, I served for 10 years in the United States Army, and I spent time in places like Afghanistan, Iraq, as well as worked with the Syrians. And the reality is that there's a lot of centralized systems, whether governments or banks or companies, that aren't just, they're not benevolent, they're not even benign, they're actually malevolent, and they're trying to oppress people, right? And this in fact gets back to one of the original ideas, political ideas, of the American Constitution. It was to enshrine individual liberty and protect individuals from the oppression of a state or from a larger group of people, right? Digital technology, this is the first time, well, not the first time. I mean, if you think about cryptography in general, it's sort of the same idea, right? So you essentially, cryptography, and by extension blockchains and cryptocurrencies, enshrine this sense of liberty in a digital way, right? So it's unlike, a lot of you guys have heard of or know of things like machine learning, big data. Those are kind of technologies which have this tendency to centralize everything to the one entity that has the data or that has the best algorithm. And so in that sense, it's kind of centrifugal. That's everything coming in, yeah, centrifugal. Blockchains are the opposite, right? It pushes all the power out to the edges and to the nodes, right? Because no individual entity is any more powerful than any other in that sense, right? Again, I don't want to get into a debate about whether or not that's politically preferable, but what I'm saying is from a digital standpoint, it's revolutionary. And I think that's one of the reasons why I'm really excited about it, and that's why I'm happy to talk to you all here today. So with that, it's the conclusion of my presentation. A couple resources I want to point you guys to. First of all, for Stanford, this is the Stanford Blockchain Club website on top. We have a Discord channel that you guys can join and hopefully participate in. I've also linked the Center for Blockchain Research. For those of you who don't know, Professor Bonet and Professor Joe Grunfest, who's a professor at the law school, they run this joint Center for Blockchain Research, and they do a lot of cool talks. So I really encourage you to check out that website. Under Learning, the top 2 links there are the 2 courses that I mentioned before that Professor Bonet teaches. And then on the bottom here, if you got, I think probably one of the most valuable things is I actually slaved over a glossary of terms for the last few weeks for my job that I mentioned earlier. So it's about 20 pages of cryptocurrency and blockchain related terms that I've tried to define in a way that's, I'm not going to say 5th grade level, but 8th grade level. So I encourage you to check that out. I just put it up as a PDF on Google Drive, so feel free and download it, and yeah, hopefully that'll clarify some questions that you have and serve as a reference for you in the future, as I hope this talk has. So with that, I'll conclude and I'll take any questions.
I guess 2 questions. One would be, what sets the market price of Bitcoin? You see the fluctuations, what are the main drivers for that? And then the second one is, in a country that doesn't necessarily provide open access to the internet, are there any restrictions on your ability to you did have cryptocurrency and be able to access it?
Yeah, good questions. The price piece, I have to tell you, if I had the answer to that, I wouldn't be sitting here right now. I would probably be trading Bitcoin for massive profits. So I think it's like many commodities, or it's like, I think the same question can be applied to the S&P 500. Like what makes the stock of a company go up or down, or what makes the index go up or down. I think there's some fundamental things, right? So for Bitcoin, for example, and again, since I work in VC, we kind of look at some things that we consider fundamental, like how many users are on the network, how many transactions are happening, how high are the fees that users are paying to transact on this network, which is sort of indicative of the demand, right? So there's fundamental things like that. But if I'm being honest, I mean, a lot of times there's just sentiment, right? Just like in regular stock investing, right? There's sometimes it's like this intersubjective sentiment that like everything's really going to go up and we're all going to be rich. And other times it's like, oh my God, this is all a scam, and like, this is hopeless, and it's, we should all sell all our stuff right now. So, in short, it's complicated. Your second question is really interesting for censorship. Actually, countries like China actually do censor internet access. But interestingly, this actually doesn't require the internet necessarily. You just have to transmit this data to other people. So there's all kinds of different ways that people actually get around that censorship in China specifically. One of the coolest ones, I think, is there's a company actually based in Silicon Valley called Blockstream, and they actually paid to launch a satellite that literally its only purpose is to beam Bitcoin transactions to and from China, right? So so literally all that's required is connection to this satellite, right? And it propagates that communication to the rest of the Bitcoin network. There's other stuff like mesh nets, which for those of you who don't know, mesh nets is it is like a peer-to-peer network, kind of like the internet, except it's like individual kind of devices that propagate signals. Stuff like that. And yeah, at the end of the day, the traffic, it's because it's secure using cryptography, and the individual traffic, if you look at the packets that go in and out, it doesn't actually look like anything different. The data doesn't look any different really than regular data that's being transmitted over the internet. So in that sense, it's pretty hard to censor. Does that answer your question? Yeah.
What prevents a single miner from monopolizing the rewards, and are miners rewarded in proportion to the amount of work that they put into a block, or is it just if they, an entire block is rewarded?
Yeah, so an entire block is rewarded, but the probability of finding a block is proportional to the amount of effort that you put in, right? So kind of like I mentioned this on the little slide with the miner guy, but essentially you're paid out approximately in proportion to the amount of work, and in this case we're talking about energy that you put into running these computers to try and solve this specific computation. So you're paid in proportion to the total contribution, or in proportion to what your contribution is relative to the total contribution. But when you do find a block, when you do add one, you're paid a set reward, which is essentially the entire block's reward. Yes?
I wonder which company is the most promising in the blockchain area currently? For example, Coinbase, Ripple, or...
Well, I'm a registered investment advisor, which means I actually can't give you that specific advice. Actually, in this venue, but I'll answer it kind of a different way. I think there's some things that I think are really exciting. Some technologies are kind of second generation things. And so one of those is actually a different type of verification mechanism or consensus algorithm for a blockchain, which uses, instead of computation, which is pretty energy inefficient, running these computations over and over and over again to use a lot of energy. There's this different proposal, which is to say that the person who gets selected to add data to the blockchain, they get that privilege essentially in proportion to the amount of the native cryptocurrency that they stake or bond, right? So it's if we imagine Bitcoin, and instead of miners doing these computations, essentially if I had 2 Bitcoin, I could choose to stake my Bitcoin and put it in some type of bond, and then according to the total percentage of, or to the amount that I staked relative to the total amount that everyone staked, I would be accorded the privilege of adding a block, in that probability, and so I would get rewards. And if I misbehaved, if I did something against the consensus algorithm, then my stake would be slashed, right? So I would lose my deposit, right? So this is like an idea that's kind of that people are playing with that actually has a lot of promise for a couple of different reasons. And I didn't get into a lot of the stuff around the drawbacks of proof of work. I mean, I think it's got a lot of great properties, but there's some drawbacks. But I think this is a system which certainly promises to be more energy efficient, but is relatively untested. But a lot of the, frankly, fundraising in like the crypto VC space is going towards projects or protocols that kind of take that approach as opposed to proof of work. So, yeah.
What do you think is beyond protocols? What are the real world applications?
Yeah, I mean,
Next step.
so I think one of the ones that I think has a lot of potential is identity. I think you could use this potentially as a means to create a decentralized system of identity. And again, I think that's something that we here in the United States just take for granted. But again, I mean, to go back to the slide of the Syrians, like, you know, I used to work with a number of Syrian refugees, and, you know, when they fled Syria, oftentimes they didn't have their passports, and now they're sitting in a refugee camp in Turkey with essentially no proof of identity, right? And what that means functionally is they have no access to any kind of aid that the Turkish government provides. They have to, like, UN aid, right? But essentially, for all intents and purposes in the global and individual country legal systems, they don't exist, right? And I think there's kind of no incentive for there to be, for a global entity to issue like an ID card, right? Like, I don't know, it would be a pretty hard problem for any single entity to do. But I think some of the applications that are being explored for blockchains is to take that same technology and essentially apply it to identity and issue people identities, digital identities that are tied to their real identities, and so essentially it's a decentralized identity system. So I think that is one potential application that I'm pretty excited about. And then honestly, I mean, this you know, even though I said it's more than finance, like a lot of the application really is in finance, right? You wouldn't believe how inefficient, like, I mean, not you wouldn't believe. I mean, who's tried to do an ACH transfer? Right? It takes like 3 days. Like, why does it take 3 days? This is 2019, right? I can send a text message and it can travel around the world 3 times in like 1 second. So there's tons of inefficiencies that a system like this can solve as well, I think, in finance. Does that answer your question?
Yes.
In the back.
Are there competitors or other brokers besides Coinbase?
Are there? Is that what you're asking?
Yes.
Yeah, no, there are. So yeah, I probably should have disclaimed. I worked at Coinbase last summer, and then, you know, I stole a slide from the CTO there. There's actually a pretty thriving ecosystem of different cryptocurrency exchanges, and they're really actually quite important players in this industry, because essentially, like, if you want to, like, for those of you that don't like own a Bitcoin or own a cryptocurrency, like if you want cryptocurrency and you have dollars, it's kind of, you know, there's no, like, I mean, it's hard to go from like dollars to cryptocurrency. That's the point of the exchanges, right? So it's like, I have dollars, I want Bitcoin, you can go to a place like Coinbase and many others, and basically make that exchange happen. And then once you're on an exchange like Coinbase and the other ones, then you can essentially transfer between digital currencies. But Coinbase is the biggest in the United States. Outside of the United States, to be honest, the majority of trading happens in Asia. So there's a lot of quite prominent exchanges in Asia. I think Binance is the biggest one by volume. But it's actually really interesting. I'm going to kind of digress for a second. The regulatory landscape around these exchanges is pretty fascinating to watch. And you know, Coinbase in the U.S. has kind of differentiated itself by following all the rules and regulations, which are quite Byzantine in the US, which apply to financial entities. Exchanges like Binance don't. They flaunt any regulation from any country. And in fact, they've re-domiciled, I think in the history of the company, which is about 2 years, 4 different times. So they started in Hong Kong, they moved to Japan, and they moved to Malta, and now I think they're in the Caymans, right? So it's sort of like this idea that, like, staying one step ahead of the enforcers or the regulators, and that's part of their strategy. And so I do think that kind of gets to the fact that, I don't know, I guess I'll use this to make the point that, like, you know, cryptocurrencies and blockchains are used for good and for bad, like any technology, right? And so I would submit in the case of exchanges like Binance, which purposefully flaunt the regulations and avoid regulators, I would say, you know, a lot of the activity that happens on there is probably illegal in some jurisdiction, right? Or is connected to some illegal activity. So, Patrick.
What's the biggest non-regulatory risk to crypto? And what's the story that you think through that, you know, crypto 10, 15 years down the line, it turned out to be like irrelevant and a fad?
Yeah, you know, honestly, I like, to answer that question, I have to just first state that I think the predominant risk is regulatory,
Sure.
like far and away. And I think that's really because of the fact that the system that I've described, for those of you who don't know how central banks work and how like national fiat currencies work, like this circumvents a central bank, right? And this, in a sense, stands in the place of a central bank. And central banks and fiat currencies are a way in which sovereign countries exert power. And so in that sense, if this were to work really like as well as the dollar, right? Let's say like, you know, it gets widely adopted. I mean, it really does fly in the face of our idea of national sovereignty, right? And so countries and governments kind of do have an incentive to prevent that from happening. So I think that's far and away like the biggest risk. Now again, like I said, I think, you know, I don't want to get into like a political philosophical discussion, right? But, you know, just because a government is, you know, a government, or even because it's elected, doesn't mean the decisions that it takes are always right or even good for the majority of people that it governs, right? And there's plenty of cases where that's the case around the world and through history. But as far as other things, I think the biggest thing would be some type of exploit or some type of vulnerability that is inherent to the code that is basically the consensus algorithm of like a major blockchain like Bitcoin, that someone were to exploit and therefore cheat the system or cheat other people out of like the currency that they had. I think that would, any kind of like hack type thing or vulnerability like that, I think would damage people's confidence so much that maybe it wouldn't be, people would just be afraid to use it, right? Because they're like, well, is this actually secure? And by the way, I think the flip side of this is I think one of the reasons why I think Bitcoin is, like, every day that it still exists is even more reason to have confidence in it, right? Because like there's, I think last time I checked, $200 billion thereabout, or actually I think more than that. No, $200 billion or so of value on the Bitcoin blockchain, right? The incentive, if you're a hacker, to like exploit that system is, I mean, $200 billion. That's huge, right? It's like the equivalent of hacking a central bank of a country. So I think so that means there's people who try all the time, and therefore the longer that it lasts, it's this idea called the Lindy effect. For those of you who don't know, it's kind of this idea that like the longer something exists, the longer it's likely to exist. And so therefore I think the longer that something like Bitcoin goes unexploited, the more confidence that people have, and therefore it's a self-reinforcing kind of thing. Yes?
To give a short general idea of the current approach of traditional VCs to crypto?
Yeah, like give an overview? Yeah. Well, there's no one answer to that question. Different VCs have different takes, and frankly, some VCs, so I worked at another VC firm before Andreessen Horowitz as well, and honestly, many of the partners there felt like this was a fad, and that it was, you know, it was kind of just for people to like buy into, and it, you know, wasn't anything revolutionary. So there are VCs who are quite accomplished who don't think that this technology is revolutionary in the same way that like AI and machine learning is. At least they don't think it's worth investing in. Maybe I should put it that way. But yeah, I think the consensus is, well, yeah, there really is no consensus, honestly. I think some people think it's revolutionary, others think it's a scam. And I think those that don't think it's a scam, that think it's potentially revolutionary, there's a whole galaxy of different communities that are oftentimes kind of built around these individual crypto projects or cryptocurrencies that tend to have quite acrimonious debates. It's one of like the really powerful things about this technology, right? It's the sense that, so for Bitcoin, right, and you know the code that runs Bitcoin is open source, which means that anybody can contribute to it, right? And you participate in the network as a miner, or if you hold Bitcoin, like you want the value of Bitcoin to go up, right? So you're incentivized to like contribute and somehow make it better at a fundamental level. And so it's got this really amazing property where it really incentivizes community participation. The downside of that is it can make people a little bit balkanized, I guess I'll put it. And so I think that's one of the things that I've noticed since being in the crypto community, that the people tend to have very strong opinions about what they think is the right cryptocurrency or right approach, and generally those opinions align with what cryptocurrencies they own. So, yes?
So if you look fast forward like 3 years from now, and let's say it's a very optimistic future for cryptocurrencies or blockchain in general, how do you think it will unfold from the adoption perspective? And how is this 3 years from now perfect future will look like? Or 5?
Yeah, I think it's probably more like 10, to be quite honest. And I think it depends on what you're measuring against, like what's your yardstick. I think if you're looking for cryptocurrency to replace Visa, that may never happen, potentially, right? Like, I think, honestly, like as I described multiple times, the really revolutionary thing about this is that you can transact or interact with people on a digital network completely trustlessly. That actually comes with the cost of efficiency, right? Like you saw by the diagram of like a peer-to-peer network, like it's relatively trivial to see that like clearly if everyone has to send messages to everyone else and everyone in the network has to verify every transaction, like that's just inherently going to be slower than a system where there's a central party that's doing everything, and if you trust them, like you can get 10x or 100x efficiency gains, right? So I think in the sense that like, I think Bitcoin to a certain extent has already succeeded in places, and I don't want to push this too far, but I do think there's evidence that places like Venezuela or Argentina or even Turkey, where last year there was a bit of a currency crisis and people in those countries didn't have confidence in the government to be good stewards of the financial system. I think Bitcoin sort of has accomplished its mission of being like this digital gold, right? It's something that you can flee to and maintain the value of your life savings that you've built over life, and that no government can like destroy overnight. Like in Venezuela's case, right? Like hyperinflation means that whatever stack of cash you have on your desk is essentially, you might as well just throw it in the fire because it's meaningless, right? And so in that sense, I think it actually already works. I think in the sense that it will meaningfully replace existing payment networks. I think in 3 to 5 years, I think it's possible that inter-country, like between country transfers, will be put on the blockchain because a lot of times there is like a trust issue between like intermediaries or even banks. And so I think that's likely in 3 to 5 years. And I think for a more broad distributed computer, maybe 10 or 15 years. And I think that'll require some technological breakthroughs around how do you overcome this trade-off between efficiency and decentralization.
And what is this distributed computer, distributed computer used for?
Yeah, I mean, like I said, it's really anything that honestly, it's not useful for anything that you could do on a regular computer, right? And that's to say that like, if you have, if you are in a group of people that all trust each other, there's kind of no reason to use it, right? But I think there's some interesting applications around like smart contracts, where like you can essentially encode the law or bylaws of the company or kind of just certain logic onto these contracts. Once these contracts are on the blockchain, they live forever, they can never be deleted, even if the people who put the code there are long since gone, right? So these things sort of exist autonomously, and then you can continue to interact via the logic that's encoded in this contract that lives on the blockchain, and you know that it's being executed exactly as it was written because of the nature of this, the architecture, right? So again, it enables this trustless interaction between people. And honestly, I think like, maybe I'll just end, I know we're out of time, and maybe I'll end on this point. Like, I just want to emphasize how incredibly amazing that is, right? Like, the potential to coordinate trustlessly across borders, between ethnicities, between individual groups of people, is something that has never existed in the history of the world, right? And like, the whole reason people like form political entities around like, first it was monarchies, and then it was like constitutional monarchies, and then it was republics and democracies, like all these systems are essentially means to get people to coordinate towards some end goal, right? you could see this type of thing, in a very optimistic world, and maybe idealistic, some might think, but this is another way for people to coordinate their actions collectively and know that every other individual in there is not cheating the system, right? And so I think that has the potential to solve all kinds of huge problems that we face today that aren't specific to any one country, like global warming is a perfect example, right? And there's many others, but so I think from a political perspective and from a public action and coordination perspective, this enables things that were never possible before. So with that, I'm going to end. We're out of time.
I have some logistics as well for events that are coming up for next week. If this got you interested, next week on Wednesday at 6:30 p.m. we have a high-level overview of Near Protocol, which is a platform that makes it really easy to develop decentralized applications or smart contracts. And then if you have some coding experience, on Thursday at 6:30, we're doing a coding workshop with Near. So if you just want to get a high-level overview, you can come just on Wednesday. If you want both a high-level overview and some coding experience, you can come both Wednesday and Thursday. And it's both at 6:30 on both days. And I'll send out emails about those two events. And then Alex also mentioned decentralized identity as a high potential opportunity for blockchain. And we're trying to get someone from Microsoft who works on their decentralized identity platform that was just announced last week. So once we get that finalized, I'll also send out information about that. And I'll send out a survey for you guys if this talk spurred any questions or topics that you'd like to learn more about, to get your input on what you'd like to learn, and we can organize events to cater to those interests. Thank you.
And please join the mailing list and the Discord if you enjoy this stuff.